The last thing I want to say about counting permutations is that when you're writing down a list of all the different cycle types in Sn, for example, it's a good idea to do it systematically so that you know that you've got all of them. So what's a systematic way of counting, of listing all the cycle types in S6? Well, one systematic way of doing it is to take the longest possible disjoint cycle you can have and then keep going where you order them starting with the longest possible thing at any given moment. So the longest cycle you can have is a cycle of length 6. The next longest you can have is a cycle of length 5, in which case the other one has to be of length 1. Now the next longest thing you can have is a cycle of length 4. Now you've got some choices. Once you've put 4 of your elements into a cycle of length 4, the longest thing you can do with the remaining elements is have a cycle of length 2. And the next longest thing you can do is 1, 1. So now we move down to 3. Once you've got a cycle of length 3, the longest thing you can do with the remaining elements is to have another cycle of length 3. The next longest thing you can do is have a cycle of length 2. And the next longest thing you can do is have 3 cycles of length 1. So now we're down to 2. If you do something of length 2 for your first one, well, we're listing these in order of longest cycle first. So we could also have, after 2, we could have a cycle of length 4, but we've already done that. So we only have to think about the longest cycle that's not bigger than this one. So the longest thing we could have is 2, and the longest thing we can have after that is also 2. And then the next longest thing we could do is we could have 2, we could have 1, 1, and then the next longest thing we could have is just 1, 1, 1, 1, and that finally leaves the shortest ones that we could have, which are the identities. So that's a systematic way of writing down all the cycle types you can have in S6. So that's all I want to say about question 1 on homework 8. I hope that you can look at the model answer and now understand how those numbers came out to be those numbers. For question 2, we had the following cycle, 1, 9, 3, 2, 4, 8, 6, 5, 7. So you should now find it very easy, most people did this fine, to find the number of, we're trying to find the number of elements in this conjugacy class, right? And the conjugacy class consists of all the elements of the same cycle type. So we just count the number of elements in this, of this cycle type. So it's sort of easiest to do the long cycle first. So for this disjoint cycle of length 6, we have 9 possible choices for the first number, 8 for the second, 7, 6, 5, 4. We've now overcounted by 6 because we could have started that 6th cycle in any one of 6 places. Now we've got 3 remaining numbers. We're doing this in S9, remember. We've chosen 6 numbers already, so there are only 3 numbers left from which to choose a 3 cycle. How many ways are there of doing that? Well, there are 2 ways of doing that. So that's the total number of things of that cycle type, and if you work that out, that comes out to be 20,160. Now, so that's the size of the conjugacy class in S9 of alpha. So to get the size of the centralizer, you've got to divide by that, because remember, by the orbit stabilizer theorem, the size of the centralizer multiplied by the size of the conjugacy class have to multiply out to be the size of the whole group. So what's the size of the whole group? Whoops, that was a bit high up on the board, wasn't it? The size of the whole group is 9 factorial, and so you've got to divide out by 20,160. So you can do that by cancelling all these things out if you want, and you discover that what you get is 18. So that's the size of the centralizer there. The thing to remember being that the size of the centralizer multiplied by the size of the conjugacy class equals the size of the group that you're working in. That's all I have to say about question 2.